Hello, in this lesson we are going to talk about NMR spectroscopy. And I know there's a lot on the page right now, don't worry about that. Let me explain how this week is going to be a little bit different in lab. I've actually released for you a filled out notes. So it's sort of a scaffold of the notes and you're just going to fill in as we go along, but most of it's already written out for you. So you can go ahead and print out the little packet right below this video that says it's the NMR notes blank. And just fill it in as we go along. And that's because this lesson is kind of long. So instead of writing everything out, I think it'd be easier to just follow along with me and just write out the most important parts. If you want to write everything down, be my guest. So NMR spectroscopy is the most important structural tool available to the organic chemist. It is by far the most sophisticated, it is the most advanced, and is the most difficult to understand form of spectroscopy, but it also gives the most information. In previous weeks, we've already seen IR spectroscopy, which could be used to identify certain functional groups. And then we also saw mass spectrometry, which could be used to weigh a molecule. But NMR is unique in that it actually tells us the bond line structure. It will allow us to figure out who's connected to who and in what pattern. NMR stands for nuclear magnetic resonance spectroscopy, and this is the same technology that's used in MRI machine. In fact, MRIs used to be called NMR machines, but the public was a little nervous about getting inside of one because of the name nuclear in there, which scared people. They thought, oh gosh, nuclear energy, this has got to be dangerous for me. But actually the nuclear is not referring to nuclear radiation, it's referring to the nucleus, and that's exactly what we're going to be looking at in NMR spectroscopy. So it involves radio waves. So this is actually the lowest energy form of spectroscopy we've seen, compared to like IR spectroscopy is relatively high energy, causes those bonds to vibrate. But in NMR, we're only using radio waves. And if you remember, what do radio waves do to matter? They cause nuclear spin flips. If you remember way back in that lecture, we went through all the different types of energy. And so because we're able to do nuclear spin flips with radio waves, we're able to get information about the nucleus. Now, not all nucleuses can be, or I guess nuclei is the word, don't say nucleuses. The active nuclei for NMR include, not everything, only some things we can see with NMR. And I'll go ahead and write this out here. We can see hydrogen. We can see carbon, but only carbon-13, which is an isotope of carbon. We can see nitrogen, but only nitrogen-15. Fluorine-19, and 31 phosphorus. These are the most common nuclei that are explored with NMR spectroscopy, but in this class, and most commonly, unless you're working with a lot of nitrogen, fluorine, or phosphorus, you're only looking at hydrogen and carbon. These are the most useful. And so that's what we want to talk about in this class. Now, what makes a nucleus active in NMR? It has to do with the number of protons and neutrons. So any nucleus with an odd number of protons or neutrons has a nuclear spin. That's why carbon-12 is NMR inactive, because it has an even number of protons and neutrons. So we need a nucleus with an odd number of protons or neutrons to have this property called nuclear spin, and with nuclear spin we can see it in NMR. So this sort of explains that carbon-12, which is the most abundant isotope of carbon, is NMR silent because of the even proton and neutron problem. But carbon-13 is okay, but it's only present in 1.1% abundance. So that means that we need our NMR machine to be very, very sensitive to detect the small amounts of carbon-13 that are present at about 1% of every carbon. So like if you have a given chain of carbons, there's only a 1% chance that any one of those carbons is going to be a carbon-13. All the other carbons will be invisible by NMR. But obviously, if you get a large sample of a substance, you're going to have a lot of carbon-13 in there, because 1% of a bazillion is still a good number. Okay, so let's take a look at the concept of how NMR spectroscopy works. The concept is that if you have a sample of an organic compound, the protons, let's say for example, inside of the nucleus, we're talking about protons here, inside of the nucleus have no orientation. So the protons are little particles, they're encapsulated inside of the nucleus of atoms, and of course the atoms are linked together in molecules. So if you were to just zoom in on the protons, you would see that they have no orientation. The protons are just sort of pointing in all directions. Now what we're going to do is we're going to apply a very strong magnetic field to the sample. And when we do that, something interesting happens. So we're turning on the supermagnet, and you can see up at the smiley face because this is awesome. And I'll show you what the supermagnet kind of looks like on the next page. But this is a super-cooled, superconducting magnet. It's one of the strongest magnets that mankind has been able to make. And it's so strong that maybe you've seen this in TV shows. If someone brings like a metal ladder or something near an MRI machine, it can suck the ladder into the machine. Anything metal, if you have a pacemaker inside your heart, the little metal bits can get ripped out of your chest. So anyone with a pacemaker is well advised to stay far away from this machine. Okay, it's a very, very strong magnet. And what that is going to do is it's going to cause the little protons inside of your sample to organize. And there's two ways that they can organize. They can either orient themselves in the easy way, which is they just point in the same direction as the magnetic field. And that makes sense, right? You're applying a strong magnetic field. The protons are charged particles. They have a positive charge, so they're going to line up with the magnetic field. They're affected by the magnet. And so one possibility is that they align with the magnetic field. There's another possibility that's rare, but possible, and maybe perhaps a bit surprising, that it orients itself in the same direction in the y-axis as the magnetic field, but actually opposes the magnetic field. It goes against the magnetic field, points towards the magnetic field. And so these two spin states are called alpha and beta. And can you try and in your head predict which one is higher in energy? That's right, the beta is higher in energy because it's opposing the magnetic field. So what we end up with is a situation that looks like this, where we have two spin states with different energies. We have the alpha spin state, which is a lower energy, and the beta spin state, which is a higher energy. The difference between these energy levels is called delta E. And this energy difference is among the order of a radio wave. So not a very big energy difference between these states. Radio wave is a very low energy form of radiation. So this is cool. This is interesting. This tells us that we can absorb energy of certain frequency. Okay, because whenever you have two energy states that are separated by some distance of energy, that means that that substance is going to absorb or emit energy on the order of magnitude equal to that delta E. And that's good because whenever something absorbs energy, that gives us an opportunity to perform spectroscopy and get information about the frequencies that are absorbed. But there's an issue here. Let me go over here. And that is that you may think, well, what information can we possibly get? All the protons are the same subatomic particle. Protons are protons. It doesn't matter if a proton in carbon versus a proton in hydrogen. All protons are protons. So isn't the difference in energy going to be the same for every proton? So what information are we going to get? Well, it turns out there's a very cool property called diamagnetism. And the delta E is not the same for every proton. In fact, it can vary due to the local environment, due to this property of diamagnetism. Let me show you what it looks like kind of in a cartoon. So in this cartoon, I know there's a lot going on here, but we have the proton in the middle. And you can tell that it's a proton because it's got the little plus symbol. And what is surrounding the proton in an organic molecule is electrons. And so the electrons are indicated by this red orbiting sort of picture here. Okay, so we got the proton in the middle and the electrons are orbiting around it. Now, if you apply a very strong magnet to this proton, what it's going to do is cause the electrons to begin orbiting in an organized direction. So the electrons that maybe were just moving on their own, kind of on their own free will, are now going to be orbiting in a very strong, organized direction. Whenever you put charges in a magnetic field, it causes them to rotate. That's a property of magnets and charges. And if you take a physics class, you'll learn all about how electric fields and magnetic fields interact with each other. But the take-home message is that electrons start orbiting around the proton in a very organized way when placed into a applied magnetic field, which we're indicating by this B0. I don't know why they choose B for a magnet, but that's what they do. Now look what happens. When the electrons start rotating, you get a charge moving in a circle. When you get a charge moving in a circle, that generates its own magnetic field. So this is kind of cool. We're applying a magnetic field to something. In response, it's generating its own magnetic field that I'm showing with the blue lines. That's its own magnet. And it turns out that this magnetic field opposes the applied magnetic field. So if you apply a magnetic field in one direction, the electrons will rotate 90 degrees, and then the direction that the electrons rotate creates a new magnetic field that opposes the magnetic field that was originally applied to it. So that means that there is now a tiny little new magnetic field pointing down by these blue lines. These blue lines are kind of pointing down, opposing the original magnetic field. And so the analogy I kind of like to think of is if you force someone to like you, you'll push them away. So kind of imagine that this applied magnetic field is you trying to force someone to fall in love with you. And you know that that never works. If you've ever tried to force someone to fall in love with you, they're going to be not interested in you at all. Okay, and that's exactly what's happening here. The magnetic field is trying to force the electrons to fall in love. They start rotating in the other direction and created a opposing magnetic field that says stay away. Okay, so now what we see here is that the protons inside of our organic molecule are under the effects of two magnetic fields, not just one. They're under the effects of a strong magnetic field. That's the one that's produced by the supermagnet. And they're also under the effects of a weak magnetic field that's called the induced field that is caused by the electrons that are orbiting the protons being affected by the strong magnetic field and creating this opposing force. Okay? So, because the protons are having two magnetic fields around them, the delta E's are slightly different for each proton based on the environment. So if the proton is surrounded by lots of electrons, we are going to call that shielded. And if you have a proton that's surrounded by very few electrons, we're going to call that deshielded. And so the incredible consequence that we have now is that slight variations in the local environment, meaning slight variations in the amount of electrons around the proton, can affect the delta E, so different frequencies are absorbed. So now, instead of all the protons singing the same song, all the protons absorbing the same frequency of energy, each proton is going to absorb slightly different energies, and it's all depending on the local environment. So this is allowing us to sort of probe the local environment of each proton, and every proton is going to come out slightly different. Okay, and so you can see here that if you have a shielded situation, a proton that's shielded, the difference between alpha and beta is much smaller, because it's a lot easier to oppose the applied magnetic field if you have a shielding magnetic field near you. It makes it less uncomfortable to point against the applied magnetic field. Versus if you don't have much shielding around you, you really have to put your head out there in the wind, and there's a big energy difference between the alpha and the beta spin states. It's also important to mention that the magnet strength matters a lot, and that the difference in energy, and this makes complete intuitive sense, is totally correlates to the strength of the magnet. In other words, the stronger the applied magnetic field, the more uncomfortable it is to oppose it, right? If you've got a really, really, really strong, convincing argument, it's really uncomfortable to disagree with that person. Let's say you're arguing with an expert debater. It's going to be really hard to counter-argue that person because you know they're so skilled and you know that they're so convincing. However, if you're just arguing against your father-in-law, you know that he's not a very good, he doesn't know many facts, and it's pretty easy to oppose him. So that's the sort of idea here with the magnet strength. The stronger the magnet, the more uncomfortable it is to oppose it. And so here you can see that if the magnet strength is 0, there is no delta E. But if the magnet strength is increased to 1.41 Tesla, which is the units that magnets are measured at, that gives you an energy difference of about 60 megahertz. It turns out at Pierce College, we have a 60 megahertz magnet. And that's because Pierce College doesn't have a lot of money, relatively speaking, because some of these magnets cost tens of millions of dollars. This magnet only costs, maybe on the order of $5,000-$10,000, still quite a bit for a magnet. And so this is kind of a cheaper NMR. So this is what we have at Pierce College, and it is so small it can fit in the desk. It just fits on top of the desk, and it looks kind of like a microwave or something. Okay, so this is the kind of cheaper NMR equipment. Now, in major universities like UCLA, for example, that have millions and millions and millions of dollars at their disposal, they can afford the 300 megahertz magnet, which costs about $5 million. And it has a much greater delta E, and so the difference in energy is much, much larger. And it turns out that the more expensive the magnet, the stronger the magnet, the bigger the delta E. The bigger the delta E, the more resolution that the spectra will have at the end of the day. So you get a higher quality image if you have a stronger magnet because the differences of the different energies are exaggerated. All right, cool. What does the NMR machine actually look like, and what does the process look like? You put your organic molecule dissolved in a solvent inside of a narrow tube. And then you put the narrow tube inside of the superconducting magnet, which looks like this. In fact, the superconducting magnet's very small. It's just on the inside. But the superconducting magnet needs to be kept very, very cold. So this whole big thing, which is about the size of a room, it's gigantic. You can see like this is a computer over here. So like this thing is like 12 feet tall, is just a giant insulating barrel that keeps the magnet extremely cold with liquid helium. So even though the whole like equipment is really small in here, the whole thing here is just designed to insulate it. You put the sample inside, and then there is a computer attached that generates radio waves and generates a whole bunch of different frequencies of radio waves and expose the sample to both the magnet and the radio waves. Okay. Now what happens is the protons inside of the sample become oriented to the magnetic field. Okay, they become oriented to the magnetic field in either the alpha or the beta state. The protons that get excited to the beta state can relax back down to the alpha state. And when they do that, they release energy in the form of radio waves. Okay, and these radio waves are picked up by the computer in the detector here. And you basically get all the different protons singing a slightly different tune. So the protons that are really de-shielded sing a really high-pitched sound because the energy difference is very large between alpha and beta, versus the protons that are really shielded, they sing a more low-pitched sound because the difference is not that high in energy between the alpha and the beta states. And so you basically have this orchestra of sound in the radio wave frequencies that is being sung by all these protons as they relax from the beta to the alpha state. Now, because all these sounds are being released at the same time, it sounds like, you know, a complete madness. You can imagine listening to an orchestra, right, of all these different instruments playing this music at the same time. And so a mathematical trick called a Fourier transform separates the different frequencies into distinct peaks. This would be equivalent to separating out the violins from the pianos, from the saxophones, from did I say piano already? I think I did. So anyway, by separating out all the instruments of that orchestra is a process called the Fourier transform, and then that finally generates the NMR spectrum. Now there's one big problem that I want to mention here, is that the sample must be dissolved in a solvent. I mentioned that, right? But the solvent oftentimes contains protons itself, and aren't those protons going to overpower the protons inside of our sample? And so there's a few solutions to this problem because it is a real problem. Solution number one is to use solvents with no hydrogens, for example, carbon tetrachloride. Or a more common solution is to use deuterated solvents. So for example, one of the most common NMR solvents is deuterated chloroform, where instead of CHCl3, it's CdCl3, where D is deuterium, an isotope of hydrogen that is NMR silent. And so there's a big money market for these deuterated solvents. And so the structure of CdCl3 looks like this. There's D2O is another one. That's deuterated water. Not H2O, but D2O. And also benzene, D6. And that has a structure that looks like this, where all the hydrogens on the benzene are replaced with Ds, and that is benzene D6. Okay, so that's a situation, that's a solution that allows us to solve the problem of the solvents interfering with the song that our sample sings. We need our solvent to be NMR silent. So we either choose a solvent with no hydrogens or a solvent that has all the hydrogens replaced with deuterium, which is NMR silent because it has an even number of neutrons. Okay, now, looking on to the next page here. What does an NMR spectrum actually look like? This is what it looks like. The NMR spectrum has an x-axis, and the units of the x-axis are in ppm, parts per million. Don't worry too much about what that means. Just know that the units are nice, they're easy, they're 0, 1, 2, 3, 4, 5, 6, so on and so forth. And what we call the right side of the spectrum is we call it upfield. And in the upfield part of the spectrum, that is where we will find shielded protons. And then on the other side, on the left side, we'll call that downfield. That will be where the deshielded things live. Okay, and then if you look at this NMR spectrum, we have a variety of signals on it. So this would be called signal A. You could call it signal 1, whatever you want. I'm just indicating that these are separate signals. And this will be signal C. You can see that the shapes sometimes have interesting peak patterns on it. Sometimes they look smooth. Sometimes they look jagged. We'll talk about that. And of course, we've got more signals down here. Okay. Oftentimes, these NMR spectra are calibrated, and they set 0 equal to the signal produced by a substance called TMS, which stands for tetramethylsilane, which has the following structure. It's silicon with 4 methyl groups on it, sorry. So that's tetramethylsilane. And you can see that the tetramethylsilane is chosen because it's very shielded. It shows up right at 0. We'll talk about why maybe tetramethylsilane is shielded. It also shows up as just a single line rather than a complicated peak. So it makes it ideal for calibration purposes. So if you ever see a spectrum with that TMS line, just know that that's how they calibrate it to set 0 equal to 0. Okay, now even if you've understand nothing so far, this next part is very important. What information can we actually get from the NMR spectrum? Number 1, we can get something called the chemical shift. The chemical shift is the position along the x-axis in ppm. So for example, the chemical shift of signal C is 4 ppm. That's it. It's just the position along the x-axis. The chemical shift tells us about the chemical environment of the proton. In other words, it tells us if the proton is in a shielded or a deshielded environment. That's the chemical shift. Another piece of information that we can get is called the area under the curve, or integration. Okay, and I should mention before I go much further, this is specifically the 1H NMR. Okay, we're going to look at carbon NMR later on, but this is specifically for proton NMR, these things that we're talking about right now. Okay, this is specifically for hydrogen NMR. The integration, the area under the curve, tells us how many protons contribute to the signal. Are there 1 proton, 2 protons, 3 protons? How many protons are contributing to that signal? That area under the curve will tell us that. And then finally, the last thing that we can get information from a proton NMR spectrum is the shape of the signal. The shape of the signal tells us the number of neighboring protons, actually. So when I talk about the shape of the signal, I mean like some of the signals have like 3 prongs, some of them have 4 prongs, some have 7 prongs. The number of prongs will give us information about the number of neighboring protons, and we'll talk about how to use that to help get information, detailed structural information about the molecule. Okay, I'm going to stop right here because I think this is a good stopping point for you to take a break and try and process everything that's happened so far. So just know that this is sort of the theory behind NMR, and this is not what any of the questions on an exam are going to look like. This is just how NMR works and what the NMR spectrum looks like. Now, take a look at the next video. We're going to start talking about something called chemical equivalence. It's going to be an important backstory to help us understand how to interpret an NMR spectrum. So now you know the theory and technology behind NMR, and check out the next video to learn more about the next steps we're going to take.